Hello everyone, welcome to the next lecture of bipolar junction transistors. In the last lecture we ended up finishing up our chapter number 6 on BJTs. Now we are going to cover the contents related to BJTs in chapter number 7 on the topics of BJT amplifiers. Mainly we're going to discuss in much more detail about the BJT amplifiers, the allowable swing voltages, and we are also going to solve some of the circuits related to different configurations of the BJT amplifiers. So let's start our today's lecture. Okay, so BJT as an amplifier. Here is a summary of whatever we have discussed. Kind of a very quick thing. Whatever we have discussed in chapter number 6. So this figure shows an NPN transistor, NPN bipolar junction transistor, right? So this is your emitter, this is base, this is collector current. So in order to operate this transistor in the active region, which the region that we used for using BJT as an amplifier, in order to operate the BJT in the active region, we want to make sure that our emitter to base junction should be forward biased and collector to base junction should be reverse biased. When the collector to base junction also becomes forward biased, the transistor enters into saturation. Okay, so we want to operate that in the active region. Okay, so here's our voltage, VBE, emitter to base, to forward bias the emitter to base junction, which is normally equals to 0.7 volts, as we have discussed in the last few lectures. Another important thing is the voltage over here, VCE, which in order to operate that in the active region as an amplifier, this voltage should be greater than or equal to 0.3 volts. We know that when VCE becomes 0.3 volts, this is edge of saturation, right? And when VCE is 0.2 volts, this is deep into saturation. So we want to make sure that this voltage should be greater than or equal to 0.3 volts in order to make sure that it is in the active region and we can operate this as an amplifier. Similarly, we want to make sure that this voltage, the biasing voltage for the collector to base junction, it should be less than 0.4 volts in order to make sure that the junction is reverse biased. We saw that at 0.4 volts the junction enters into the forward bias condition, so we want to make sure that it is less than the 0.4 volts. For the collector to base junction, we saw that this is approximately at 0.4 volts, so we want to make sure that whenever it is less than 0.4 volts, it can be considered as a reverse bias condition and we can operate this transistor in the active mode. Okay, so this figure is a BJT NPN transistor operating in the active region. So the important thing over here, the collector current, our collector current is proportional to the biasing voltage VBE of the emitter to base junction. So this voltage controls the collector current by this value. So this is a voltage controlled current amplifier. Okay, now let's look at the circuits over here. We have seen similar circuits for the MOS-FET as well, and we have done this discussion in much detail earlier, so we're going to be slightly quicker here. So what we ended up doing is we had a voltage controlled current amplifier. However, we are interested in making a voltage controlled voltage amplifier, so we pass the current through a resistor and quantify the changes associated with the current to get the voltage values. So we ended up putting a resistor RC here. So whatever the changes in the VBE, those changes will be reflected in IC, and those changes will be reflected in the voltage across RC. So rather than taking the voltage across RC, we are taking our output voltage over here is across the collector to emitter. This was done to have a common ground in between input and the output and to make a circuit more simpler. However, if you will write the equation for this thing, your output voltage VCE should be equals to VCC minus ICRC. So whatever the changes because of VBE changes will result in changing the collector current. That will change this product value ICRC, and that will be reflected in the changes in the VCE. So this is why we can also take an output across collector to emitter and can still use it as a voltage amplifier. So it's a voltage controlled voltage amplifier. Now let's look at the second plot here. This is our VTC voltage transfer characteristics. Now you can see that on the x-axis we have input voltage, right? So this is your input voltage, VCE, this is your output voltage. So you're making any changes in the VBE will be reflected in the changes in the current and corresponding changes in the product ICRC. So our output will change. So input is VBE, output is VCE. Okay. Now let's look more closely at this voltage transfer characteristics, right? So this characteristics curve has three regions. We have a cutoff region, we have an active region, and we have a saturation region. We want to make sure that we will operate the amplifier, this BJT amplifier, in the active mode in between this line segment A and B. Other important things to look over here, our point B is the edge of saturation. Our edge of saturation over here is 0.3 volts. We saw that over here while discussing, right? So our VCE, when VCE becomes 0.3 volts, this is edge of saturation. And when VCE becomes less than 0.3 volts, even 0.2 volts, this is deep in saturation, right? So when this will further go down to 0.2 volts, we see that our output should lie somewhere over here, right? So this is deep in the saturation. Now let's look at the cutoff mode. So whenever our base to emitter voltage is less than 0.5 from this voltage transfer curve, this means that our emitter to base junction is reverse bias. So whenever emitter to base junction is reverse bias, there will be no collector current and our transistor will be cut off. So we want to make sure that we are operating our transistor in the active mode of operation. Okay, so this is what we have here. So this is the equation that I wrote earlier as well, right? So this is the output. VCE equals VCC minus ICRC, and our collector current is given by this. So IC, we can put this collector current over here in this equation. All right. So VCE equals VCC minus IS, VBE, or VT. Now we can see that here is our output voltage, here is our input voltage. And this curve is our voltage transfer characteristics of the input and output. Some other important things that we can see over here, looking at this active mode of operation, looking at the line segment A and B, that it is that this entire line segment A to B is a nonlinear amplification. So our amplifier is a nonlinear amplifier, which can also be seen by looking at this exponent value, right? So we have this exponent value over here. This means that our amplification will be nonlinear. So how we can obtain the linear amplification, and we are going to discuss it in more detail and some of the discussion is very similar to the MOS amplifiers as well, right? So if you want to make sure that we will have a linear amplification, so essentially we can obtain it by making sure that our input signal values are small enough that once amplified we are still in the active mode, and and our nonlinearities will be very small. We are going to find a condition for the small signal operation as well in the next lecture. Okay. All right, so the take-home message over here is that you connect a resistor here, RC, to convert our voltage controlled current amplifier to a voltage controlled voltage amplifier. Here is your voltage transfer characteristics. You want to make sure that we operate the transistor in the active mode in the segments A and B to operate that as an amplifier. This is a nonlinear amplification. In order to obtain the linear amplification, we should do this in a small signal operation. And we will find the small signal operation condition shortly. Before doing that, let's find out this gain value. So in order to find out the voltage gain value, we can find this voltage gain value out by looking at this curve again, right? So essentially, we know that our VCE is output and VBE is input, right? So the voltage gain would be the slope of this value, right? So the slope is a voltage gain. Voltage gain will be delta V naught over delta VI So delta VCE over delta VBE will be the voltage gain, right? So this delta can be we can easily find out by taking a slope or the derivative of this curve. All right. So here is your if you take a derivative of your output with respect to the input VBE, you're gonna find out the value of the voltage gain, which is essentially slope of the voltage transfer characteristics in the active mode of operation. So our equation was for the VC, our equation was this. So let's use this equation. This is our equation, right? So let's find out, let's take a derivative and we can evaluate, we can kind of figure this thing out. Okay. So this is your, I'm going to do it over here. So you have d VCE over d VBE equals, if I'm going to take a derivative of this thing with respect to VBE, this will be 0. If I'm going to take a derivative of this with respect to VBE, it will come out to be E VBE over VT as is. My multiplication factors are as is, and then what I will get is what will be the derivative of VBE over VT will be 1 over VT. So what I will end up getting is IS E VBE over VT RC over VT. And now this thing is our regular collector current. So we get minus IC RC over VT, voltage gain. Okay, great. Again, this was the collector current, IS EVBE over VT, which we ended up replacing over here. So this is the value that we got. Now we have an overlapping thing, but essentially the value is the same. I can write this value over here. Minus IC RC over VT, and I'm gonna rub this. Oh, sorry. Okay. Okay, what? Sorry. Okay, let's do this thing again. All right, this is the value of the voltage gain that we ended up calculating over here. AV equals minus IC RC over VT. So this is the value of the voltage gain that we have. Okay, so our voltage gain value, right? So one interesting thing that you can see over here is this thing, right? ICRC. So the voltage gain can also be expressed as, especially in the last slide, we know that our value of VCE was equal, our value of the VCE was equals to VCC minus ICRC. So we can easily express this thing as, all right, so we can easily express, we can take out this minus ICRC over here. So it will be equals to minus, our new voltage gain will be equals to minus into ICRC, which will be equals to VCC minus VCE over VT. So this will be the new value of the voltage gain. One interesting thing that we can see over here is, if, for example, what will be the maximum value of the voltage gain and how we can find it. The maximum value of the voltage gain will be when our VCE will be minimum, right? The maximum value of the voltage gain will be when this value that is being subtracted from VCC will be the smallest or minimum. What is the minimum value of the VCE that we can have in the active mode of operation over here? Right, the minimum value that we can have is 0.3 volts at the edge of saturation. So we can put down this condition to find out the value of the voltage gain. So our voltage gain, our maximum voltage gain will be equals to minus VCC minus 0.3 volts divided by VT will be the maximum value of the voltage gain that we will get. Okay, which is over here. All right. So let's do one example as well today, which will hopefully clear up more things, and especially these regions of operations, cutoff, active, and saturation, and what are the allowable swing voltage values. Okay, so let's do this example over here. Okay, so this is a circuit, and this is an example. We have an amplifier circuit of a bipolar junction NPN transistor. The scaling current is 10 to the minus 15 amperes. The resistance value RC over here is 6.8 kilo ohms. Supply voltage is 10 volts. Okay, in the first step, I want to find out this bias voltage, right? Required to operate the transistor at VCE. So we have a voltage of the VCE given 3.2 volts, and the bias voltage VBE, we need to find it out. Also, we need to figure out the corresponding collector current, right? So in order to solve this example, we wanted to find out at what is the bias voltage for the emitter to base junction when our collector to emitter bias, resulting collector to emitter voltage at that bias voltage will be 3.2 volts. So this bias voltage indicates that our time varying component can be 0 for the A part. Okay. So let's start with finding the collector current first, right? So collector current should be very simple. It should be VCC minus VCE over RC. VCC minus VCE over RC. VCC is 10 volts. Minus VCE is 3.2 volts. RC is 6.8 kilo ohms. So if you will solve this, the answer that you will get is 1 milliamperes. So this will be the value of your collector current. All right. So let's find out the value of the VBE now. Okay, so we can find out the value of VBE very simply. We know the value of the collector current. We know the value of the scaling current. And using this equation, we can find out the value of the VBE. So our collector current is 1 milliampere. Scaling current is 10 to the minus 15 amperes. Thermal voltage is 25 millivolts at room temperature. So we can easily figure out the value of VBE, right? So we have this. In order to solve this exponent, you know that you can easily take a natural log on both sides, and then solve this thing. So if you take a natural log on both sides and solve this thing, the answer that will come out to be 690.8 millivolts. So this is the value of the bias voltage that we apply to obtain the output voltage level of biasing output voltage level of the VCE as 3.2 volts. And our collector current will be 1 milliamperes. Now, second part of the question is, first, let's find out the value of the voltage gain. First let's find out the value of the voltage gain. So our formula for the voltage gain is this: VCC minus VCE over VT, right? So AV equals minus VCC minus VCE over VT. VT again 25 millivolts, VCC 10 volts, VCE is 3.2 volts. So using these three values, we can easily figure out the value of the voltage gain. So 10 volts, 3.2, and 25 millivolts, right? So this is 25 millivolts converted into volts. So the answer that will come out to be minus 272 volts by volts as a voltage gain. So it is amplifying your input signal by a value of 272 times. All right. Now, second part of this question is, if we have an input sine wave of 5 millivolts peak amplitude is superimposed on the biasing voltage VBE, what will be the amplitude of the output signal, right? So what we are interested in finding out is, rather than now this VBE to be 0, so the peak value of VBE is 5 millivolts. If this is a peak value of this time varying signature that is superimposed on this VBE, what will be the amplified version of it at the output? We know the amplification factor 272, so just multiply 272 with the 5 millivolts, and that should give you an answer, right? So our VCE, the peak value of the output time varying voltage at the collector to emitter output, will be amplification factor 272 multiplied by 5 millivolts. So the peak voltage value of the time varying signature will be 1.36 volts. Okay, now we have another part of this question that is also very interesting. Okay, so now we are interested in finding out what will be the change in the value of the VBE that will drive the transistor to the edge of saturation. We want to find out, so we want to make sure that our transistor is operating in this region A and B, right? So we are interested in finding out what is the value of the VBE, or what is the change in the VBE that will result in the transistor go to exact at point B, or the edge of saturation. In order to find out the value, we know that at the edge of saturation, our VCE equals 0.3 volts. This is at the edge of saturation again. So essentially, we're going to do exactly the same things again. First, we are going to find out the value of the collector current. IC equals VCC minus VCE over RC. 10 volts minus VCE now is 0.3 volts over RC, 6.8 kilo ohms. So we can find out the value of collector current, which comes out to be 1.617 milliamperes. So what we are interested in is, initially in the first part, when our VCE was 3.2 volts, our collector current was 1 milliamperes. So what we are interested in finding out is the change in the value of the VBE when our collector current changes from 1 milliamperes to 1.7. If you remember the diodes lecture, we can find out the values of the changes in the voltage with respect to the changes in the current by using this formula. So if you will use this formula where your V2, now you are interested in finding out the change in this. So natural log, this is 25 millivolt. Natural log of I2, 1.617 milliamperes over 1 milliamperes. If you're going to solve this, you will know the value of the VBE, or the change in the voltage values that are required when the collector current will be changed from 1 milliamperes to 1.7617 milliamperes. So the change in the or the positive change, this, and since the value is in positive, so this will be a positive increment. So the change of the positive increment that is needed in the base to emitter voltage value will be 12 millivolts, and this change will result in moving this transistor to the edge of saturation. Now we are interested in the other side of the story. We ended up finding out how to move to the edge of the saturation. Now let's figure out how to move it to the cutoff. And we want to figure out, rather than moving to exactly to the cutoff, we are moving to 0.99, 1% of the cutoff value. So if our cutoff value was 10 volts here, and we want to, so question says that it should be 1% of the cutoff, right? So what we are interested in is not cutting off the transistor, but reaching very close to the cutoff value, or the 99% value of the cutoff voltage. So if that is 10 volts, then the 99% should be 9.9 volts. Okay, so our new value of the collector emitter will be 0.99 volts. I'm going to do exactly the same thing now. Your collector current IC will be now equal, your collector current will be equals to 10 volts minus 0.99 volts divided by resistance 6.8. You can find out the resistance. VCE no, sorry, yeah, so your VCE was equals to 1% of the yeah, so it should be 9.9 volts, not 0.99 volts, 9.9 volts, right? So again, we can go back and look at that. We wanna reach to a 1% of the VCE value, which should be 99% of the VCC value. So the 99, if our VCC was 10 volts, then the 99% of the 10 volts should be, our new value of the VCE will be 9.9 volts. Okay, so our new value of the VCE is 9.9 volts. So for this value of the VCE, 10 minus 9.9 over 6.8, the answer will come out to be this. And we can use a similar formula over here. Now we are again interested in finding out the change in the VBE, base to emitter change for value, when our current will change from 0.0147 to 1 milliamperes. and the change will come out to be minus 105.5. So this is the negative increment. This is the increment that is needed that will make or move the transistor to the cutoff or very close to the cutoff condition, right? So in the previous part, we were somewhere over here, we ended up finding the value that will move the transistor to the edge of the saturation, and then we ended up finding a value that will move the saturation or the negative increment that will move the transistor to the cutoff region. Okay, so this is it for today's lecture. In the next lecture, we're gonna discuss more about the small signal operation. We're gonna derive its condition, and we're gonna derive some more expression for the voltage gain values and the currents during the small signal operation. All right. So with that, thank you so much. I will talk with you in the next lecture. Okay. Thanks. Bye bye.